Okay, we got a metal ball right here. Somebody's going to pull it up to the side till the string is horizontal. They'll let it go. It's going to swing down here. It's going to wrap around this cylinder, and they want to know how fast the ball is going. Well, it's wrapping the string around the cylinder when it's up here. So the velocity when it's all the way up there. Let's draw a before and after picture for this situation. I'll put the cylinder down here in black, and then the string connected to the ceiling directly above it. But in the before picture, it's been pulled up and to one side. I don't want the before picture to be before the person starts lifting it, because the person is putting some energy into the system, and I want to use that special case of conservation of energy where the total mechanical energy, the kinetic energy plus the potential energy doesn't change, plus the gravitational potential energy. So I'll use this for my before picture. We've got to choose a reference level, and in this picture it looks like, just even judging from this picture right here, it looks like this would be a convenient reference level right here at the level of the cylinder. So let's see if I can draw a horizontal line at the level of the cylinder. I'll label that my reference line. I can say then that initially the initial height of the object above the reference level is just how high this point is above the center of the cylinder, so that's equal to h. And in the after picture, the metal ball will have been let go. It'll swing down, the string will wrap its way around the cylinder, and the metal object will be up here with some velocity called v prime. So v is equal to 0. The person releases it from rest, and my velocity in the after picture, the magnitude of the velocity anyway, I'm going to call v prime, which is what I'm solving for. In the after picture, it's going to be at a height y prime, which I should be able to figure out from the geometry. It's going to have, there's a total length L. Part of it is just to extend down to here, and then there's a piece right here. It wraps around half of the cylinder, so that's going to be half the circumference of the cylinder. So that'll be a known length, and whatever is left over is going to be how high it is in that after picture. In fact, let's work on that. To me, it's kind of the hard part for this one. So I'm going to say I'll write an equation that the total length is equal to the length of this piece, which is h, because the point where the string is attached to the ceiling is a distance h above the center. So that brings us right down to here. Probably ought to be a little bit more careful with where I put that bottom of the bracket. So it takes us right down to the reference level. That's h, and then this piece that I've the length of the blue string, which I've indicated in red, is we'll call that let's not give it a name. It's 1/2 the circumference, which is 1/2 of 2 pi r, where r is the given radius of the cylinder. This is r. That was given up here. Cylinder of radius r. This is the cylinder of radius r. Okay. Plus it's labeled right here. So that distance that I've got in red there is just pi times r. So L is equal to h plus, put it all in blue there, plus the pi r plus the y1 prime. That gives you the whole length of the string, and I can solve that for y1 prime. I think I just wanted to call that y prime. Yeah, this was just the tail of my arrow going here. Let's make that a little bit more obvious. So this total distance is what I'm calling y prime, not y1 prime. Alrighty. So y prime is equal to L minus h minus pi times r. I'm going to need that. Now, I think I'm in a position, now that I got the geometry figured out, of applying the conservation of energy for the special case where the total mechanical energy isn't changing at all. U plus k equals u prime plus k prime. Can I cross anything out? In the before picture, it's released from rest, so there's no energy of motion. In the after picture, it's up high relative to what I chose for the reference level, and it's moving, so I can't cross anything else out. Alright, so let's go replace the u with what it is, mg times the height in the before picture, which is h. And that's equal to, actually I think I'll call it y for now, and then call that a replacement. Mg y prime, just so I'm consistent over here, I want to start out with just the y prime there, plus 1/2 m times v prime squared, or v prime is what I'm looking for. If I divide both sides by m, I get m over m in every term, which is 1. So I can just cross out the m's. I got to solve this for v. I think I'll multiply by, no, I think I'll do it one little tiny step here. Just move this over to there and switch sides. So really 2 little tiny steps. 1/2 v prime squared equals gy minus gy prime. Alright, now it's just got to do a little bit of algebra. Just an algebra problem from here on out. So I'm going to factor out the g over here. G times y minus y prime. I think I'll, before I forget about it, I'll substitute what these y and y primes are. Yeah, v prime squared equals g, and then up here, let's see, we got y is equal to h, and y prime is L minus h minus pi r. So h, and then minus, I think I'll turn this into a square bracket so I can use some parentheses inside. Okay, minus y prime, which is L minus h minus pi r. Got that right here. Simplify it a little bit more. I'm going to multiply both sides by 2, 2g, and I'll also play around with the inside here. So we got h minus L minus minus h, which is 2h. I think I'll start with that. 2h, and then plus pi r. minus L. So V prime equals the square root of 2g times 2h plus pi r minus L. And that should do it for the final answer for the velocity at the top. Square root of 2gh from working with these kind of problems, I know that comes out to be a velocity, but just to make sure, every term in here is indeed an h, or is indeed a distance, which in SI units would be in meters. So the units work out. Let's see, the higher our starting position is above the cylinder, the greater the speed's going to be. That makes sense, and that's a little bit surprising. The greater the radius is, but then we got to subtract off the length there. So I think the answer makes sense, and the units work out. We'll call that the solution to problem SAC 102, number 5.